Hello, everyone. It's Mr. Wolf here, and sad that I'm not going to be in class today. There's a family event that I'm attending tomorrow, or today if you're watching the video. But I wanted to make this video to go over and introduce some of the concepts that you're going to be working with today. So if you see the first page of your Constructing Explanations packet, that PDF is on today's section of the Google site. You'll see that it's filled out here in the video. And that's because this is actually the exact same page that we worked on Friday. Okay, so we did this on Friday. It was kind of its own separate document. It was called LT6 Foreshadowing, but it was really just the first page of our packet. And if you notice here, it says level 1. So these are kind of where we break down some important concepts that will build up to our eventual explanations. Okay, so a few things just to kind of go over this is, let's see, scenario 2 talks about Happy Gilmore putting a golf ball. The first one travels slow, the second one travels faster. So it says to draw your LOL, so it's traveling on the ground. And I drew 2 blocks of K here, 4 blocks of K here. So for the first putt, I drew less K because I'm going to use this equation. Right? What variables contribute to kinetic energy? It's mass and velocity. And so in this case, the big thing here is golf ball, so same mass, is it has a smaller velocity, the first putt, so I drew less K. Right? So really what you're doing is you're saying why you drew something, like you drew something, and then why did you draw it? Right? So it's always a physics concept. So describing your model, why did you draw that? All right, so that's what page 2 is going to look like right here. Very, very similar stuff. Right? Remember how we modeled work right here, right? We're going to use the equation work equals force times distance for that. Right? And then here, it's still kind of a similar thing, but instead of just looking at like one box between two scenarios, we're going to look at the whole LOL between two scenarios. And these LOLs are almost completed, but you'll notice that this final L has not been completed. So you're going to see how you should draw these different LOLs based on what's already been drawn. And then again, explain why you drew it this way. Not really using an equation, but just using this general concept of the law of conservation of energy. All right. And then we're going to get on to this other section called practicing concluding statements. All right. So concluding statements are going to be how we wrap up our explanations. And in fact, what I'm going to do is I'm just going to go to page 5. This is our first example explanation right here, where it might ask us a question, how are the velocities of these cars going to compare at the bottom of the hill? And we'll look at more of the scenario in a little bit, but what we'll do is we're going to draw our LOLs, we're going to write our explanation, say what we drew and why we drew it for each part. But then at the very end, we need to kind of wrap it up to talk about our claim. So this is going to be our concluding statement right here. So I'm going to go back here, and I'm going to run through the first 2 concluding statements. So I'm just giving you a scenario here. 2 cars are traveling with kinetic energy of 100 joules. They both have equal masses. How do their velocities compare? So whenever we're writing a concluding statement, let's say if I'm talking about velocity, well, what variables associated with velocity? K. So I'm going to talk about this equation. And then I'm going to look at my 3 variables that are involved here and see how, I'll always know 2, and then what would that other variable be? So in this case, we know that the kinetic energy is 100 joules, it looks like, for each one. 2 cars are traveling with a kinetic energy of 100 joules. So I'm going to box in K. That just kind of tells me it's the same. And then they have equal masses, so my masses are going to be the same. So then my question is well, how are their velocities going to compare? And hopefully this kind of seems a little bit obvious. Well, like if everything is the same and the only variable that's left is velocity, shouldn't they all be the same? Yeah, it will be. So you could actually say that, where you say, because these cars have the same kinetic energy, same mass, they would have to have the same velocity. I'm fine with that. Here's another template that I think is helpful, especially when things change. But we could also use it for this one too. So I might say kinetic energy. Right? Kinetic energy. You could just put K2 as constant. So if mass, stays the same, then my only other variable that's left, velocity, would also have to stay the same in this case. So let's look at an example where things are actually changing. So let's say Harry Potter Book 1 and Harry Potter Book 6 have the same potential energy, but Book 1 is higher. How do their masses compare? All right. By the way, we don't need to mention G because that will always be the same on Earth. So I wish there was a little bit more space when I made this. But one thing I like to do is I kind of like to draw out, let's do like book 1 and book 2. And what I'm going to do is I'm going to write out our equation, because if I'm talking about potential energy and height, I'm going to be using UG equals MGH. So for number 1, Harry Potter book 1, it says that they have the same potential energy. So I'm going to draw UG. I put number 2 here, but this is book 6. It's a much bigger book. So UG. So same potential energy. So I showed that by boxing it in. And that's going to be equal to, it says book 1's at a higher height. So by the way, how I'm going to represent that is I'm going to just draw a bigger H right here. And then a smaller H here. So we're still dealing with equations, but a little bit more conceptually now. And then, by the way, G is always going to be the same, so you can include it or you don't have to include it. I'm going to include it, but I'm just going to box the G in, showing it's the same. So now the only variable that's left is mass, right? So it's this idea that, okay, potential energy, UG is constant. So if, let's look at like book 1, let's say that's what we're talking about here. If book 1's height, so if height increases, right, then what's going to happen to mass? Well, my mass would have to go down, right? If this is going to be a smaller height, right, this mass would have to go up in order for both of these scenarios with different masses and different height to still equal the same potential energy. Now, you don't have to write these equations out to write your concluding statements, but they can be really, really helpful, and I actually always do this. So again, if potential energy is the same, but this has a greater height, right, the way that this still is going to give me equal potential energies if this has a smaller mass. So then mass decreases or is less than, all right? Now, by the way, this works out mathematically too. Most of my students like doing it like this, and I do too, but some students like have a mathematical mind, and they're like, okay, well, I know potential energy stays the same, so I'm going to put in a 1 here, and I know the G stays the same, so I'm going to put in a 1, and then the height, well, that's bigger, and they don't really tell me a value, but I'm just going to put in 4, because that's a larger number, right? And this height's smaller, so maybe I'm going to put 1/4 in, because that's a smaller number. So in order for everything to equal 1 at the end of the day, well, 4 times 1 to equal 1, this would have to be 1/4, right? 1/4. And then here, in order to equal 1, 1/4 times 4, all right, I'm just going to make this a little bit bigger so it's easy to see, all right, would have to be my mass. So again, if I compare these, same potential energies, different heights, my mass, 1/4, 4, would have to be smaller, would have to decrease in order for this equation to work out. So that's an example of a concluding statement. What you guys are going to do in just a sec is you're going to work on the concluding statements for number 3, and then on the next page, the scaffolds are taken away, but you're still going to decide, like, all right, if I'm talking about velocity, what energy is related to that? If I'm talking about distance or force, what energy is related to that? And then you're going to base everything off your equation, your concluding statement. Now remember, you're also going to be working on these two on page 2. But what I want to do now is I want to give an example of what an explanation would actually look like. Okay, so this is going to be on page 5, and we have 2 different scenarios. And instead of kind of going, well, I could read through it real quick. Actually, instead of reading through it, Mr. Bozade made a video explaining what's going to be happening. So let's just watch that instead. So here's the setup to the problem that I was just showing.
This time, we're going to take this car and we're going to release it on a certain height. Let's say right here, this height right here, okay? And we're going to measure the velocity at the bottom. Ready, set, go. There we go. Now, we're going to take that same car. By the way, this is a frictionless car, so there's no friction. Tires are not taped or anything like that. Okay? And instead of releasing it up here, we're going to release it down here. How will the new velocity compare to the old one? Will it be faster, slower, or the same? I imagine you can guess. But can you use your knowledge of physics to explain how the new velocity is? That is your new challenge. LT6 is explanations. And you've got to figure out how to explain some of these phenomena using your words and your knowledge of physics. Good luck with that.
All right. So I'm going to go back to the video now. So I was drawing this while he was doing his setup, by the way, and you feel free to draw this too. But scenario A, so everything's the same. The only different, and by the way, these are frictionless Matchbox cars, we essentially say. Right? Friction is negligible. The difference, though, is the height. So here we have a height of h, and here we have a lower height. So that's the only difference, is we're just dropping this from a lower height. And our goal at the end of the day is circle the claim that answers the question, how will the velocities of the frictionless Matchbox cars compare at the bottom of the ramp? All right. Now, I think intuitively, like Mr. Bosaday said, you guys could probably be like, all right, well, for scenario A, it's higher up, so it's going to be faster for scenario A. I mean, we could probably do that intuitively, but the goal is to use our concepts of energy to explain why that actually is the case. Okay, so let's first start off by drawing our LOLs here. All right, here we have no. I'm going to ask the question: is there velocity at the top? So this is the top of the ramp before they let go. No velocity, so no K. Right. And then let's see. There it looks like there's some height, so I'm going to have UG. All right. And I'm going to start making my LOL. And you guys, I think, have a pretty good foundation in drawing these. But with explanations, now what you're going to do is you're going to say, why did you draw those the way you did? And that will allow you to make a conclusion at the end of the day. So what I mean by that is we're always going to start off with, or two components, kind of similar to our graphs, is our physics concepts is our physics concepts, and then describing our model. Okay, so when I say physics concepts, why, like for instance, the model we drew no K, right? So I'm going to say like no K. Why did we draw no K? Right? Oh, well, like that was because like cars have no velocity, right? That's why we did that. That's our physics concept behind the model that we drew, right? And then for our potential energy, well, we know there's height, but specifically it looks like they have different heights, right? So I'm going to draw maybe 3 energy blocks here, and let's just do, let's do 4 here, and let's do 2 here. So I'm going to say, for describing my model, there's more K, more UG. This is in UG, obviously, right? So more UG. All right, so why did I draw more UG? All right, for car A? Well, that's because car A is at a higher height, right? So car A is at a higher, I'm running out of room, so I'm just going to do H for height. And that's why I drew more UG. If we go back to the first page, that's exactly what we're doing here, right? They have the UG's equal because they have the same height and mass, or the kinetic energy I drew less than because it has a smaller velocity. All right? All we're doing are these, but just a bunch of times and in a broader context for some type of scenario. All right. So I've drawn my first LOLs, and now I'm going to move on to the scenario to see if I'm going to have any work going in or out. So remember, the question for work is always going to be, is there an outside force? All right. And it says here that we have these frictionless Matchbox cars, so no, if there's no outside force, that's not going to cause work to go in and out. So that's exactly what I'm going to say. Right? I'm going to say, hey, no outside forces. Or I could say no friction. Either one of those works. No outside forces. So, these arrows, by the way, are just kind of so. No work. And that's it. I'm just explaining why I didn't draw anything here. And then now I'm going to just work on my last L's, where I'm like, okay, here I have UG. Nothing goes in or out, so, well, it's at the bottom of the hill, so is there height? No. Is there velocity? Yes. And we know that there would also have to be energy in K because